Yeah, hello and welcome to the PML School. My name is Bernd Wendt and I'm here with my colleague Chris Mehl, and we are going to run our this 17th session of the PML School. So we've covered already a lot of grounds from support questions in the previous 16 sessions, all of which you can access through our Certara forum. And after this session, we have 3 more sessions to go until we go into a summer break. Today I will be speaking about a pharmacodynamic example, and I will be talking about a turnover model. For this type of model, we typically receive many questions in support, so we want to make sure we are covering all the different aspects in our PML School sessions. And as usual, this example has been taken from the book of Gabrielson and Weiner, where this example is called PD7, that book. We will make available the model file and the slide deck, as well as the recorded session to our forum after the event, from where you can pick up everything. During this session, if you have any questions or comments, please use the Q&A console on the right-hand side of the WebEx. And later on, after the presentation, Chris Mehl will also run the Q&A session where we directly respond to your questions. So our objective for today is as follows. So we have response time data, and we want to model this with a turnover model, and this is after IV infusion, dose ranging study. And here we want to find estimates for this model, that is a K-in, a zero-order turnover rate, K-out, first-order fractional turnover rate, and Emax, the maximum response, and EC50, the concentration at half maximum response. Okay, move on. The problem specification, 3 sets of constant IV infusion experiments were run with increasing doses in a group of patients. The infusions were done over 4 hours time, and the response time data was obtained thereafter. And the pharmacokinetics of the drug was determined beforehand. So we've got the PK parameters for this. It's best modeled with a 1-compartment model and with a volume of distribution of 28.6 liters and an elimination rate constant of 2.8 per hour. So we only have PD data, that is response time data. What we need or what we want to do is to simulate the PK to get some PK profiles as well. How do we do that? Here's the setup. We use the Phoenix model object for that, and we are only using the built-in options. Let me show you. So we've got a PK type of model. In this case, because we know the elimination rate constant, we use a microparameterization. We've got IV absorption in 1 compartment. And since we know this is an infusion, so we check the infusions possible checkbox. And with Phoenix 7.0, you can also specify the duration of the infusion rather than the infusion rate, which was required previous to Phoenix 7.0. And then we stick with an additive residual error model. But since this is not a fitting, we need to go to the Run Options tab. Here's the Structure tab, and we switch to the Run Options tab. And here we switch to Simulation. For the simulation, you have to specify the number of points that you want predictions for, concentration values for, and the time range, the maximum X range, which is a time axis, 8 hours. And what the predicted parameter that we want to get calculations for is C. This will run the simulation once executed. We don't need to specify dosing separately. You will see that in the demonstrations. This is coming with the data set itself, and I will show you in a demo how to deal with that. What we get out of this is then simulated profiles, PK profiles for the low, medium, and high dose. So you see over the period of 4 hours the infusion, and then the drug is getting eliminated quite quickly. These are PK profiles, and now here below, this is the actual data that we want to model. This is our PD data, and you know, these are the same time scales here, what you see between PK and PD, but you can see that there's not a really linear relationship between the PK profiles and the PD profiles. Also, you could expect maybe some delays in the response relative to the PK concentration of the compound. So this is why we need to model this with a turnover model. But let's have a closer look here at the PD response data. So you start at a baseline level of around 30, and then the response drops over the infusion time and stays at a constant over the while, over the infusion time, and then steadily goes back to the baseline. Maybe just a very slight difference is when you see this is a low dose, medium, and high dose, you could somehow see that the time it takes to get to the steady state, if you will, is getting shorter from when the dose increases. And that indicates that maybe the stimulation of the loss is the right model to pick for this particular data set. But let's come to that later on. This is to complete the exploratory analysis. This is a response concentration data with a concentration on a log scale. And you see the typical hysteresis loop. So we are starting here with a baseline value of 30. Concentration increases and the response decreases, and then while the concentration stays the same, the response decreases further and then goes back to the baseline again. The same for the 3 dose levels. So we have to deal with the delay between response and concentration. That's why we need to model this with turnover model. This is the schematic diagram of the turnover model with stimulation of loss. So this is a response, and it gets produced with a turnover rate of Kn, and gets eliminated with fractional turnover rate K out. But then we apply a drug with an Emax model, Emax and EC50 values, which models the decline of the response. But next one. So how do we start with the model? As we said, stimulation of loss, that's what we want to model. We stick to population mode in this case because we've got 3 dose levels, and we want to fit one data set, one set of parameters for this model. And we use the different dose levels as an ID differentiator here, or ID variable in this case. The model type, we switch to PK indirect. This is the PK part up below that, so we leave that as is. But we want to freeze the PK for this PD fit. Now for the indirect model, you have this option, so you can pick from an option here to switch to stimulation limited. And here you can switch between build-up and loss, and so we switch to loss in this case to really model the stimulation of loss. For the residual error model, we'll just stick to with the additive model. This is how we set up the model. It's really just the built-in options. We don't need to change anything on the graphical model, and also we don't need to change anything on the textual model. But let's just go through this. So you see here these three different or alternative representation of the same model. This is what I just explained, the built-in options, and this is how it looks as a graphical model. You see on the left-hand side, this is the PK model, one compartment with an elimination compartment, and the concentration of the plasma in the central compartment is connected with the E block, the response block, where we use Emax, EC50, K-in, and K-out as parameters. And the model is fit through an observation, the effect of observations, which will run the fit. This is a graphical model. And here is the corresponding PML code, that's the textual model. Let me switch over to look at this in more detail. We are dealing actually with two differential equations. The first one for the one compartmental model with IV input. So here again, typically we specify this with amounts, but I'll just use the volume in order to show this as a concentration, the change of concentration over time. That equals the input minus the elimination rate constant times the concentration. And when you look at this, and you can easily enter this into PML code just like that. It's just instead of concentration, we are dealing here with amounts A1. But that's we are scaling that back in the next line. C equals A1 over V, so we are scaling down the amount to volume, to the concentration. This is for the PK part. The PD model looks like this. Also as a differential equation with K-in minus K-out, where the stimulation of the K-out is here represented with this type of Emax model. And that you can see it's just written in PML code as is. But it's really the same line that you have to enter here. And then you have set up your turnover model. After that, you have to initialize your response. And here we are using this equation that E0 equals K-in over K-out. So this is the sequence statement is just there for specific steps that can be run at a certain time point during the fitting, and this is run just initially. So E at the beginning is actually K-in over K-out, and the parameters K-in and K-out we have as initial estimates here in the parameter block, in the fixed effects block. As I said, the residual error model is additive, so we just use this EPS equals 1, and the observation is the predicted effect plus this residual error. So for the fixed effects, we have two PK parameters, volume and KE, with the estimates, and then 4 PD parameter, Emax, EC50, K-in, and K-out. So, before we go into the demo part, just we need to get some ideas about initial estimates that we can use to set up the model. So for K-out, we just take it from the initial slope, and you will get this around 1, a value of around 1. K-in, you can take it from the equation E0 equals K-in over K-out. We just rearrange it and get the value out of this, which is 30. And next is Emax. That's the maximum effect. That is, you can take it from the plot, roughly 4. Now for this EC50, we have to express the turnover model in a steady state equation. This is done here. And we just take steady state parameters from the plot. For example, for the low dose, we have a steady state concentration around 20 units and effect around 13. If we enter this into the formula, we get to a value for EC50 as initial estimates of around 40. Okay, so let's move on. Yeah, now we come to the demo part. Let me share my Phoenix application. Chris, can you see the screen?
Yes.
Yeah, looks good, Bernd.
All right, thanks. So this is a data set. We've got time, response, the dosing group, and this is a typical format where you specify the dose with your data. It doesn't have the right units, so it's just unitless. You see we've got 3 dose groups and the corresponding response time data. So the first thing we do usually is to send it to a plot. Let's just make this plot. So we put time to the X, response to the Y, and we group by group. And this is the plot that you've seen from the slides. We just make it a little bit wider so that you see the curvature. So now the first step was that we want to create some PK profiles for our PD data. And this is, for this actually, we need one additional information. We've got the time, the response, and the dose. We know it's an infusion, so we need either the infusion rate or the duration. And that's what we need to add to this data set. That's easily done through a data wizard step. So I'll just send the data set to a data wizard object and just call this add duration. Okay, and here we need, as an action item, we need a transformation step. And we say add this. So this will appear. And as a transformation type, we specify a custom transformation and give this a new column name called duration. And we say if the dose is larger than 0, give it a 4. This is a duration time, 4 hours. Otherwise, keep it empty. This is what it is. Now we've got a duration for each of the different dosing groups. That's what we need to run the PK simulation. So we send this to a Phoenix model object. And here we go down to the bottom. In this case, we don't want to run a population analysis, so we uncheck this box. It's a PK type of model. We have microparameterization, so we need to switch it here. It's intravenous and 1 compartment, but we don't want to use a closed form. We just want to use differential equations. This is an infusion, and so we check infusion possible, and we want to specify the infusion with the duration parameter. That's it. Now we can go to the run options, and here we just say, okay, I want to run a simulation. And as I said, I would like to have maybe 80 points calculated over the time range of from 0 to 8 hours, and it's the concentration I'm interested in. So that's that. Now we need to look at the main mapping on the top. Time is already mapped. We don't need response. We take group as a sort key. We've got 3 different dose levels, so 3 different groups. The dose is A1, the infused amount, and duration is A1 duration. And with that, we can start the simulation. You may see these warnings here. There's an optional main column C ops is not mapped. We can ignore this for the simulation. So we can just simply run this. And takes a little while, and now we've got the simulation results here in this worksheet, 80 points, and the plot is here, right, with increasing dose levels. What we want to do is, in order to create the hysteresis loop, we want to join the original data with a simulated PK profile so that we can create a response concentration plot. So we can send this to a data object join worksheets. And here we need to specify which of the input from one worksheet matches with the other one. So a group should match, and IVA, this is an independent variable, this would be time typically, should match, and DV, this would be the predicted concentration. This should be a source column that should be taken with the new table. Worksheet 2 would then be our original data, where time and group would be the sort keys. Those should match between these two worksheets. And response and dose we just want to take with us. Now we have different column names, column headers. So for the sort map, we need an internal worksheet. So in this case, we need to make sure that time matches IVA. So we just move it up so that IVA is time and group is group. Also, we are just interested in a smaller table, so we just want to do an inner join that only was all matching sorts. It will create a corresponding table, and that's what you see here now. We have the group, IVA, time, this is a concentration, this is a response, and the dose. And this we can now send to a plotting object. We group by group, take time as X. Oh no, sorry, this is response over concentration, so we take dV, which is our concentration, to X, and response to Y. We execute this, we get this. All right, this is not a true hysteresis curve. Let me just unsort the X values, and you see it looks much better now. Now we need to work a little bit on the X-axis. We just want to see from 1 to 1000 logarithmic form. Wait a second, there's something wrong. Oh, just a second. I must. This is a PK simulation. I missed to enter the fixed effects. As this should be 28.6 from the slides and 2.8. So these were. You need to provide this information to run a proper simulation. Let's do this. And then we'll just execute the plot once again. Now this looks much better. So we just want to don't show markers, don't group by line, and maybe also expand this a little bit. So this is now our hysteresis curve. Now what we can do now is to actually run the PD model. So we can just copy our PK simulation object and paste it back to the workflow, and now we can say this would be our PK PD model. Okay, everything else stays the same. We just need to change the type to PK indirect. Also, as I said in the beginning, we have 3 dose levels, but we only want to get one set of PD parameters. So we set this to population so that we can move our group variable to the obligatory ID column. Also, we want to freeze PK. So, and we just focus in this fitting process on the indirect and on the turnover model. And here you can choose between the different options. We set stimulation limited of the loss of the response. No shape parameter, so we don't take an exponent. And we stick with the residual additive error model. What we have to do here now is to map the response to the effect observed, EOBS. So that's it. We should now look at the initial estimates. Going to the initial estimates. It will produce the first curve here. And here, as we said from the slide, K in should be around 30. K out should be around 1. Emax 4. And the IC50 was around 40. And we can use the overlay to see all three curves at once. And you see this already matches very well the curvature, that is the data points. So this we can just say, okay, accept, accept. And then we go to run options. We don't have any random effects, so we can go back to naive pooled. So this is all, so no individual variability is considered here. And run the fit. Okay, so here's our model. Let's first look at the fit itself. Here's our fit. Again, we want to see it a little bit more wide. And here you see the fit. You see the data points scatter around the regression line, the line, the predicted curve. And that's for all three dose levels. So this is really a very nice fit. Just looking at the fixed effects, the theta table. See here our estimates, not too far away from our initial ones. And the coefficient of variation is also reasonably low. So this is a very nice model and a very nice fit. Yeah, that was a very quick example, quick model. You know, we just had to deal with the built-in options, but nevertheless, this is a typical PD model that we use for those circumstances, situations. So just a summary, we built this turnover model. What I showed you is if you don't have the PK data for the turnover model, you can easily simulate a PK profile using the parameters provided. And then you can turn your PK model into a PD model. You freeze your PK parameters, and then you fit the model and look at the results. This is, once again, just the results to show you really the nice fit, once again, of the data and the final theta table, the final estimates for the different PD parameters with the statistics on the right-hand side. With that, I guess we are at the end. So I guess it's time for Q&A. Chris, you want to take over?
Okay, Bernd, could you maybe go over the initial estimates again? For some of the people might have joined a little bit late and not seen those. And so, first of all, the model selection was stimulation of loss. What drove that, and then how did you get the initial estimates?
Okay, yeah. Stimulation of loss. I mean, this is for this data set, and when you look at this one, and this has been covered in previous sessions already. With PD model, when you try to model response time data, you have quite a few options. You can use an effective compartment, a link model, if you will. You can use an Emacs model, or you can use a turnover model like we did here. But what you can easily see is that this is a non-linear relationship when it comes to when you compare the PK profile with the PD profile, and you see it's going down here this way and stays at a certain maximum level, and you see it somehow approaches here a maximum effect, Emax, at the bottom. So it, when you go from low, medium to high, so this might be really the maximum effect that you can exert. And simulation of loss, I mean, you can also try, if you have an indirect model, you could also try an inhibition of production, inhibition of input. This would be the alternative choice. And if you don't know, exactly, and if it's not as clear as here, I would go and, run the inhibition of input next to the stimulation of loss turnover model, and then compare the outcome. What is a better fit? But what is clearly seen here is that when you increase the dose, the time to steady state shortens. So when you look at the model, where's the model? Wait a second, one further. K out is now stimulated with this function. When I increase the dose, this term gets larger, and so for the half-life of this gets smaller, and so the time to this steady state, or to this reaching this Emax, will get short, and that's what you can observe here in those lines, coming from low doses to high doses, and that's why I shoot it for the stimulation of loss. What you could do, and what I did as well, because I mean, if you've got time, you simply run it through. You can run an inhibition of input model with this data set, but you will find out that it doesn't do a nice fit of just this part of the curve, because it cannot really match the different half-lives, if you will, to reach a steady state. Okay. Chris?
Yeah, thanks, Bernd. So that wraps up the Q&A session.
Okay. All right, and thanks, Chris. Let me just go to the next slide. What's coming up we've got 3 weeks time until our next session that Chris Mehl will present a turnover model 1, repeated dosing 1. This is 1 week later because of the 4th of July week where people are on vacation. So hope to see you back on July 13th. Thanks for your continued interest, and yeah, we'll see you there. You may disconnect now. Thanks.